Hello, I'm Baek Seong-Eun, a master student at Amiral. So today I will introduce post-hoc probabilistic vision language models, and it will be introduced at iClear 2026. So first, it is not enough for models to only provide the prediction for decision. So if it only outputs predictions, as shown in the example, uh, incorrect decisions can lead to serious problems. Therefore, we expect the model to also quantify the uncertainty of its predictions. So by doing so, we expect that they can make more rational decisions based on how confident the model is in its answers. So, like this, uncertainty is especially important in safety critical domain, like autonomous driving or medical diagnosis. So, and certainty has also been widely used in active learning, where humans label only highly uncertain data. So various methods of uncertainty computation have been proposed. So most of them focus on calibration, fine-tuning, and the test time adaptation. However, these approaches have limitations in real-world settings. So they often fail to capture epistemic uncertainties when handling unseen data, or they require significant additional computational cost. Then, how can we estimate uncertainty effectively? So for this, the authors define 4 requirements. First, the method should be model agnostic. So this means it can be applied to any VLM architecture. Second, it should be efficient with almost no computational overhead during inference time. Third, it should be effective in accurately estimating uncertainty. And finally, it should be training-free, requiring no additional training. So this work proposes BayesVLM, which satisfies all 4 of these requirements. So BayesVLM uses the Laplace approximation to estimate the Bayesian posterior, and it then drives an analytical expression called the prob cosine, which propagates the distribution of probabilistic embeddings to the final output. So as a result, BayesVLM reduces errors caused by overconfidence and provides more reliable uncertainty estimates. So this scenario refers to cases where incorrect predictions occur despite the low reported uncertainty, which we define as overconfidence. By estimating uncertainty through BayesVLM and performing zero-shot classification again, it encourages the high uncertainty to be assigned to incorrect predictions, increasing the likelihood that the model can say, I don't know, when they are not sure.
Oh, is it different?
Oh, yeah. Without a basic VLM, this region have a lot of points rather than these regions. So overall, uncertainty trend is moved to that regions. So the contributions are as follows. So authors propose BayesVLM, an efficient and effective post-hoc method for uncertainty quantification in VLMs. And for they first proposed the direct Bayesian formulation of VLMs and derive a prob cosine. And they also demonstrated the efficiency and efficacy of a BayesVLM in both zero-shot setting and active learning setting. So I will explain how BayesVLM is implemented. So before the main method, first explain some preliminary. So the pre-training of VLMs is conducted by minimizing the info-NC loss like this. So this encourages similar image text pairs to be positioned close to each other, and the unrelated pairs to be positioned far apart. So through this process, effective learning across modalities become possible. And the next background knowledge is about Laplace approximation. So when performing Bayesian deep learning, the posterior is estimated like this. However, in practice, the marginal likelihood induces a high-dimensional integral like this, so making it intractable. So therefore, the authors apply Laplace approximation, which approximates posteriors without directly computing it, and like this. So this theorem consists of three steps. Step one obtains this term through likelihood approximation, and step two computes the covariance through Hessian approximation. I described the overall process of Bayesian VLM. So first, after the image and the text pass through the encoders, and the Laplace approximation is applied, resulting in probabilistic embeddings. And the distributions of these embeddings are used to estimate the expected value and the variance between embeddings, which generated a distribution over cosine similarities. This cosine similarity distribution is propagated so that the VLM output reflects uncertainty. So Bayesian VLM process in three steps, and step one approximates the likelihood. So to construct the Bayes VLM, we first define a likelihood function. The challenge is that the loss functions used to train VLMs entangle modalities and the data points. So this violates the independent and identically distributed assumption required for Bayesian modeling. Therefore, to satisfy the IID assumption, two independent probabilistic models are assumed for each modality. So for in image input cases, the encoder produces an image embeddings, which is multiplied by a matrix H hat whose rows consists of text embeddings. So this allows us to compute the losses for each text candidate corresponding to a single image. So by applying a softmax function, we obtain a probabilistic model for the image input, and the likelihood becomes a categorical distribution. So once the likelihood is approximated, the mean of the posterior under Laplace approximation can be obtained. And next, we need to compute the Hessian matrix to obtain the covariance of the posterior. But calculating the full Hessian is practically impossible. So therefore, BayesVLM introduces the generalized Gauss-Newton approximation called the GGN approximation. So this reduces computational complexity, but the encoder of a VLM contains a lot of hyperparameters. So GGN approximation is only applied to the final projection layer of the encoder. So the Hessian matrix can be approximated as follows. But authors adopt the Kronecker factor the GGN approximation to reduce computational cost further. So expressing the Hessian as the Kronecker product of two smaller matrices like A and B. And this Kronecker product can be rearranged as like this. So allowing us to compute the covariance for the image input. So through this process, posterior estimation via Laplace approximation is complete. There isn't enough time to go into a detailed derivation right now. So if you have any follow-up questions, I will answer them later. And we can obtain like this posterior distribution. So step 3 is about how to utilize the estimated posterior during inference time. So unlike the original VLM, BayesVLM produces the probabilistic embeddings. Therefore, instead of the standard cosine similarity, prob cosine is proposed to measure similarity between distributions. So the formula for prob cosine is given as follows, like this. So which provides a local Gaussian approximation of the cosine similarity distribution. So we can obtain the distribution of our cosine similarity like this. And by incorporating the variance into the prob cosine computation, the uncertainty within embeddings can be propagated to the final output. So now I will explain the experimental result. Before explaining result, I briefly introduced the evaluation metrics like this. So accuracy evaluates predictive performance equal classification performance, and the NRPT evaluates the quality of the estimated probabilities, and the expected calibration error evaluates calibration quality. So in NRPT cases, lower NRPT is better, and EC cases, EC measures the gap between confidence and the actual accuracy, so lower is also better. So when evaluated on benchmark related to uncertainty estimation in zero-shot settings, BayesVLM demonstrates effectiveness by maintaining similar accuracy while achieving improvements in NLP and C. So this result is BayesVLM. So they can get similar accuracy compared to other baselines, but they can get lower NLP and the ECE for across all benchmarkers and compared to other baselines. And furthermore, when applying prob cosine to probabilistic VLM trained from scratch, so consistent performance improvements are observed. So mean means standard prediction of probabilistic VLM models. So when we apply the prob cosine in them models, we can get lower NLP and similar accuracy compared to standard baseline. And compared to the qualitative results with ground truth, so black line is GT and the blue line is estimated approximation through prob cosine. So the approximation error is low, confirming the effectiveness of prob cosine. And when applying BayesVLM for sample selection in active learning, the tendency toward overconfidence in correct predictions is reduced. So when combining BayesVLM with EPIC, higher accuracy is achieved while maintaining lower NLPD, demonstrating that effective sampling in active learning is possible. Another experiment about active learning on Eurosnet. So without BayesVLM, overconfidence persists even after active learning, like this. But In contrast to with BayesVLM, not only does overconfidence decreases, and after overconfidence decreases after active learning, and the overall model performance improves through more efficient active learning. So to summarize, this paper proposes BayesVLM as a novel approach for post-hoc uncertainty estimation, and this enables analytic approximation through prob cosine, and to demonstrate the effectiveness of BayesVLM through experiments. So this is the end of my presentation. Thank you for listening.